In this video, we're going to look at a new way of calculating our enthalpy, delta H. We've already looked at it two ways. We've looked at it where we calculated all of the energies of the individual molecules, and we looked at products minus reactants. And then we've also looked at Hess's law, where we found individual if you will, steps in the reaction mechanism, where we looked at like maybe reaction 1 plus reaction 2 yields reaction 3, which is our product reaction. And maybe we flipped one of the equations and multiplied it by a certain equation. But in the end, we were still trying to calculate the same thing, which is our enthalpy for a reaction. And so in this video, we're going to calculate this enthalpy a new way, where you may have a chemical that's more complex. And so when you go look it up in the table, you can't find the enthalpy for that specific molecule. Or maybe you don't know all the different ways that we can get there with other reactions. And so if that's the case, you can use what bonds make up the molecule to calculate the enthalpy of that molecule. And then you can just look at the whole equation and take the bonds broken and subtract the energy of the bonds formed, and that's going to be your enthalpy for the whole reaction. And so in this example, we're going to do just that. We're going to calculate the enthalpy of formation for this reaction. Now before we get started, we need to note two things. One, is this balanced? It's not. You need to balance it. Two, do you have a list of these average bond energies? You should have a table somewhere. And so this is our table in our textbook. And one thing that's interesting is there's an asterisk on the C double bond O. One is a C double bond RO that's not in our carbon dioxide. And then one is C double bond O that is in carbon dioxide. So for this equation, we're going to use the C double bond O that goes with carbon dioxide. So it's 799 as opposed to the one without is 749. All right, so let's do these. So pause the video right here, balance this equation, and then come back. All right, when you balance this equation, you should have gotten 2, 7, 4, and 6. And now that it's balanced, the first thing I want us to do is, in order to figure out which bonds are broken and which bonds are formed, you got to draw the Lewis structures, and you all know how to do that. So now that you know how to draw the Lewis structure, we can answer this question and say what bonds were broken, which bonds were formed. And so try and stop, pause the video, try and draw a Lewis structure for each one. And then do one more thing. If it says 2, draw 2 of them. If it says 7, draw 7 of them. I know that's a pain, but go ahead and do it. So pause the video right now and give it a try. All right, welcome back. You should have now drawn all the Lewis structures for each of these molecules. Now, some of them are a little more complicated with the C2H6. You got your 2 carbons in the middle and all the hydrogens drawn around it. For the oxygen, O double bond O, and there are 7 of them. Okay, and then here, carbon dioxide, you have 4 of them. C in the middle, the least electronegative with oxygens on both sides. And then, of course, our water molecule, all important water. All right, so if we're going to do this reaction, we're going to take bonds broken to form. So which ones needed to be broken? Are we breaking these bonds or are we breaking these bonds? You're breaking the reactants, and you're using that energy to form our reactants, okay? And so you're taking our bonds broken minus bonds formed, because remember, when you form a bond, you're releasing energy, and so that energy is negative. And so these enthalpy values, we're going to subtract them. The important thing is it says bonds broken. So it's not just, hey, we have one C to H bond, let's take 413 minus 495 minus, you have to take every single bond broken. So it looks more like this. Delta H equals, how many C to H bonds do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I have 12 C to H bonds, and that energy is 413. Okay, I'm going to go ahead and just do a little C to H above it so I remember. Plus, what other types of bonds do I have? If I move straight to here, I will have forgotten about my C to H bonds. How many of those do I have? I have 2. So plus 2 times C to C, which is 347. And I'm going to denote that C to C right above it. All right, next, now we can get into our O to O. Plus our O to O double bond, which is 495, and there are 7 of them. 7 times 495 minus all of that, minus the bonds that I have formed. So how many bonds have I formed? If you said C to O, so how many of those do I have? How many C to O's do I have? Do I have 4? No, you have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 of them. So minus 8 times C to O, which is, since it's a carbonyl, I'm using this value, or not carbonyl, sorry, carbon dioxide, I'm going to use this value, minus, now I go over here to water, O to H. How many of them do I have? There are 6 molecules. That's why I had you draw it out. Do you have to do that every time? No. I was just drawing it out so you'd remember there are 6 molecules. That means there are 2 of these O to H bonds in every single molecule. 2 times 6 gives me 12. So I have 12 of these O to H bonds. And so this was O double bond O. This one is C double bond O, and this one is going to be O to H. So now we have laid all of this out. This is all of the math, and now it's just a matter of putting all of this into your calculator, and we end up with, I'll break it apart into one step for you. Delta H is 9115 is all my positives, minus 11,996, and that equals negative 2,881 kilojoules. Now you might ask, I thought it was kilojoules per mole. Well, this per mole are these numbers, the 12, the 2, the 7, the 12, and the 8, because that's how many moles of each type of bond you have. And so the moles cancel and you're left with kilojoules. Let's try another example. Let's do this one next. It's a little bit easier than the last one, so I want you to try and do it on your own. Balance it, draw the Lewis structures, predict the average bond energies, and then come back to this video and see if the calculated enthalpy value that you came up with matches the one that I came up with. If you balance this equation properly, you should have had 1, 3, and 2 to make it balance entirely. And now let's draw the Lewis structures. Nitrogen would be N triple bond, another N like that. There's one of them. Hydrogen is H to H. There are 3 of those. And the last one is NH3, N bound to an H with a lone pair, and there are 2 of these. So now that we've drawn our Lewis structures, let's put them in this equation. Enthalpy is bonds broken minus bonds formed. Broken, formed. So delta H equals, how many moles of broken bonds do we have? We have 1 mole of these N triple bonds. N triple bond is 941 kilojoules per mole, and I'll put a little N to N triple bond up here, plus H to H, 3 of them. So 3 times 432 minus my formed bonds, which is here, 1, 2, 3, 4, 5, 6. 6 of them times my energy, which is 391. All right, now you just put that in your calculator and see what you get. You should have gotten enthalpy values of 2,237 for the positives, minus 2,346 for my negatives, my bonds formed, and a total enthalpy change for this reaction of a negative 109 kilojoules. Negative energy released. All that stuff still applies.